Welcome to The Explainer. Today, we're taking a trip, not across the globe, but zooming way, way down into the hidden microscopic world inside an ion chromatography column. If you've ever wondered how on earth chemists manage to separate a wild, complex chemical mixture into completely invisible ionic components, well, the secret is all in the stationary phase. We're going to completely demystify these highly engineered materials today. Let's get right into it.
Here's our quick roadmap for today. We'll start inside the chromatography column, then look at engineering synthetic copolymers, customizing the chemical surface, the modified silica approach, layering with film resins, and we'll wrap it all up with the final analysis.
All right, Section 1, inside the chromatography column.
So this really begs a fundamental question, right? What actually separates the tiny, invisible ions in a chemical solution? We're dealing with molecules we literally cannot see, just rushing through a tube under intense pressure. How do we grab onto specific ones but let the others just breeze right by? Whether we're testing municipal water for safety or purifying proteins, the magic all comes down to the microscopic engineering of that solid material packed inside the column.
Okay, let's dive into this. Early stationary phases were pretty much just basic resins used to deionize water. But today's materials are incredibly complex. They have to survive a brutal environment. Basically, any modern stationary phase has to meet some seriously strict requirements. First, microporosity, meaning they need a massive internal surface area. Second is granular metric distribution, which is just a fancy way of saying the particles have to be perfectly uniform in size. Third, and this is absolutely crucial, mechanical resistance to pressure. The liquid mobile phase is being forced through there at crazy high pressures, so these little beads absolutely cannot crush or deform. And finally, stability under extreme pH conditions, because they're constantly bathed in superacidic or superalkaline solutions.
Moving on to Section 2, engineering synthetic polymers.
So, the absolute heavy-duty tool in our toolbox here is the cross-linked polycoproner. Usually we're talking about a matrix made of polystyrene and divinylbenzene. Imagine forming these incredibly hard polymers into perfect, tiny little spheres. We're talking just a few micrometers in diameter. To put that into perspective, that's literally a fraction of the width of a human hair. Because they're cross-linked, they become super rigid, totally able to resist that massive pressure inside the column without collapsing.
Now, what's really interesting here is how this cross-linked polymer matrix essentially acts as the physical structural core for the resin. It's kind of like the sturdy scaffolding. But as you probably know, a sturdy scaffolding by itself doesn't actually separate ions. To do the actual chemical heavy lifting, catching and releasing those specific ions from the mobile phase, we have to go in and chemically alter that physical structure.
Which brings us right to Section 3, customizing the chemical surface.
Think of these surface modifications like, well, chemical Velcro, tailored to grab very specific molecular shapes. We can tweak these hard polystyrene spheres in two main ways. For a cationic exchange, we use a process called sulfonation on the aromatic nuclei of the polymer. This creates a strongly acidic phase where the anion is permanently fixed to the macromolecule. This lets it reversibly catch and exchange cations, giving it an exchange capacity of a few millimoles per gram. On the flip side, if we want anionic exchange, we start with chloromethylation, basically binding a CH2Cl group, and then react it with a tertiary or secondary amine. That creates a basic phase where the cation is fixed, making the surface completely perfect for exchanging anions. And the best part? Both of these setups stay incredibly stable over a massive range of pH levels.
But before we move on from polymers entirely, there's another really cool alternative in the toolbox, acrylics. By copolymerizing a mixture of two acrylic monomers, where one is anionic or cationic and the other is polyhydroxylated, we end up with a stationary phase that's highly hydrophilic or water-loving. The catch? Well, they do have a variable swelling issue depending on exactly what's in the mobile phase. Because of that swelling, you'll generally see them reserved for medium-pressure chromatography and specific biochemical applications where that water-loving trait is just an absolute must-have.
All right, Section 4, the modified silica approach. To build this particular hybrid solution from the ground up, we take a step-by-step approach. Step 1, we start with porous silica particles. Step 2, we support those particles with alkyl phenyl chains. And finally, Step 3, we use covalent bonding to attach our active exchange groups, things like substituted sulfonated or quaternary ammonium groups. What makes this modified silica approach so incredibly useful is that it compounds the perks of different techniques.
The separation here isn't just relying purely on ionic exchange, it's actually leaning on both ionic coefficients and the partition coefficient. That gives us a highly nuanced separation mechanism for really tricky complex mixtures.
Moving to Section 5, layering with film resins.
Okay, to really grasp this next concept, I want you to picture a continuous chemical film that is just astoundingly thin. We are talking 1 to 2 micrometers thick. It's an almost impossibly delicate layer, but it does literally all the heavy lifting when it comes to ion exchange. Now you might be wondering, how on earth do you manufacture a chemical film that thin and actually expect it to survive those high-pressure liquid flows?
Well, it brilliantly comes down to a layering technique. You start with a large, hard support core, usually a 25 to 50 micrometer sphere made of silica or polystyrene. On top of that big core, a polymer called latex, which carries organic functional groups, is deposited. But here's the kicker. The latex isn't a liquid. It's actually made up of tiny little spheres themselves, just 0.1 to 0.3 micrometers across. These tiny latex spheres bond to the large support core through polar bonds, and then the remaining double bonds go through a hardening process called reticulation. The end result? You get this rock-hard core totally enveloped by a continuous, ultra-thin, highly reactive ionic film. It's honestly just a masterpiece of microscopic engineering.
And that brings us to Section 6, the final analysis.
So the main takeaway here is that a modern chemist isn't just stuck using one generic stationary phase. They have this highly specialized, microscopic separation toolbox ready to solve real-world problems. If we need something exceptionally hard and stable across wild pH ranges, say for testing industrial runoff, we reach straight for the cross-linked polycolomers. If we're tackling biochemical work and need a hydrophilic environment at medium pressure, acrylics are absolutely the way to go. When a really complex separation calls for a blend of ionic and partition properties, we deploy the modified silica. And for incredibly efficient, rapid surface interactions, we use film resins, layering that ultra-thin latex over a hardened core. Every single one of these microscopic structures is perfectly matched to its job in the lab.
Which leaves us with a pretty thrilling prospect, right? We've seen exactly how chemical engineering at the micrometer scale can neatly separate the invisible chaos of a complex solution. But as our manufacturing techniques get even more precise, and as we engineer even smaller, smarter chemical architectures, what new molecular mysteries will these microscopic stationary phases unlock next? The boundary of what we can separate and discover is literally only limited by the ingenuity of the stationary phase itself. Thanks so much for joining me on this explainer, and keep that curiosity going.